measurements. Thank you. For today's lesson, I have prepared a picture. And based on this picture, I want you to guess the topic that we are going to discuss today. Mina, based on the picture that I have shown you, I want you to guess the topic that we are going to discuss today. Do you have any idea about it? Very good, Fermina. You were able to guess the lesson for today. That's right. Our lesson for today is motion. I want to share to you our target for today. At the end of the lesson, 100% of you who are attending this class must be able to have at least 75% level of competency, must be able to define the basic keywords related to motion, define the basic concepts related to motion, and be able to derive the important formulas using the concepts. And then, finally, we should be able to apply these concepts in problem solving. As you have guessed, we are going to study motion in one dimension, and later on, if we have still time, we're going to continue the discussion in the two-dimensional aspects. But before anything else, we are going to discuss the difference between scalar and vector quantities. Quantities are very important in the study of physics. Let's start with the scalar quantity. These are quantities that we measure that possess magnitude but does not possess direction. Some examples of these are volume, density, mass, speed, energy, and time. Alright, so vector quantities, on the other hand, are quantities that we measured that has both magnitude and direction. Like, so for example, acceleration, momentum, force, velocity, and weight. In regards to this, I want you to complete the table of vector and scalar quantities. I'm doing this for you to understand and explore other things that we measured in physics. Moving on, go to the basic definition of motion, which is motion is the change in position with respect to a certain reference frame. Let's say, for example, you are traveling from your home or your house going to your school. Alright, so your house or your home will be your reference frame. And once you go to your school, there is now a change in position. Now, distance is defined as the amount of length that you have traveled. Let's say, for example, you traveled from your home, which is your reference frame, to your school. Now, you're going to get a meter stick or a tape measure or a certain surveyor to measure the distance, and you are going to measure it in meters. Now, let's say how fast or how slow you have traveled. Are you running? Are you walking? Are you jogging? So this rate is defined as your speed. Alright, so it is the measure of how fast or slow an object is moving. Another quantity that is related to our study of motion is the quantity of time. So time is the measure of the time interval when the motion started and ended. In short, it is a duration period. Alright, so let's say, for example, you have your clock and you look at it when you are about to leave your house. Alright, so you measure it. Let's say, for example, that is 7:30 a.m. Then you walk towards your school, and you reach your school, and you look again at the clock. Alright, and you found out that it's almost 8 a.m. So the time duration from 7:30 to 8 a.m. is the time that has passed by when the motion started and ended. Tricky concept that you have to put in mind is the concept of displacement. This is different from distance. Displacement is a vector quantity, while distance is a scalar quantity. We define displacement as the absolute position from the initial position to the final position. As you can see, there is a rectangular lap, and we have its corners. We name it point A, point B, point C, and point D. Let's say you travel around from point A to point C. And the sides of the lap are as follows. So we added, and we found out that the distance we have covered is 10 and 20. Alright, so the distance covered is 10 meters plus 20 meters. However, the displacement is the directed distance from point A to point C. So we are going to get the hypotenuse. Alright, so because that is the directed distance. And you can use your distance formula or Pythagorean theorem. So that's the basic difference between distance and displacement. Okay, so I hope everyone can follow. Right now we are ready to deal with the equations that we need to describe motion. You cannot just say that you're fast, you cannot just say you're slow, but you have to quantify it. So in doing this, we need the formula for speed, which is defined as distance over time. So distance, as you have known, this is the amount of distance you have covered, and it is measured in meters, and time is the total duration of motion. From this initial equation, we can actually get an equation for distance which answers the question how far you have traveled. So we have d is equivalent to speed times time. How much time has passed by? Suppose that you wanted to know the time that you have consumed during your trip, you can use the formula t for time is equivalent to distance over speed. Speed, as I've mentioned, is a scalar quantity, however, velocity is not. Velocity is a vector quantity. So you can write velocity is equivalent to v, which stands for displacement as of this point in time, over time. We're ready to define the concept of average velocity. So average velocity is defined as the ratio of the displacement of an object per unit time. So we have average velocity, VATE, is equivalent to d, which stands for the displacement over time. Alright, so displacement is related to the change in position, which can be related to 2 points, like say for example, x of 2 minus x of 1 all over time, or the time that has passed by, or the change in time. Say for example, p sub 2 is the final time, and p sub 1 is the initial time. Alright, so in case that these informations are not available to us, instead, only the initial velocity and final velocity are available, we can use this formula. Alternatively, average velocity is equivalent to initial velocity plus final velocity all over 2. So these things here, or formula over here, are derived using algebra, and this one is formulated using statistics. Suppose that you wanted to win in a race against someone. All you have to do now is to step on the gas pedal, and you will gain speed. And the moment you gain speed, there is a change in speed. Let's say for an initial velocity, which is slow, the final velocity, which is a little bit faster or fast enough. And now we can define acceleration as the change in velocity per unit time. So the changes in velocity, namely Vf, or the final velocity, minus initial velocity all over time. And here is your formula. The formula for the final velocity is Vf is equivalent to Vi plus At. I'm going to show you a quick derivation of this. Define the average velocity using the formula for Vf and substitute it here. And we will get average velocity now is equal to 2Vi over 2. Then later on we will cancel 2 plus A times T all over. Okay, so we go ahead and simplify the formula that we have just derived. And once we do that, we will get, and then we can substitute the concept for average velocity as displacement over time, and we equate it to the formula. Alright, so we cross multiply time to the other side, and we will get D, or displacement, is equivalent to VIT plus A times t to the power of 2 all over 2. You can actually use the formula d is equivalent to x sub 2 minus x sub 1 and substitute it right here. Alright, so we can get the final distance and we can regard it as x sub 2. Alright, so once we transpose x sub 1 to the other side, and we will get x sub 2 is equal to x sub 1 plus vi, which is the initial velocity times time, plus a times t to the power of 2 all over 2. If you have any clarifications about the lesson, you just can go back and watch the video again. Alright, so let's put these things into practice. Make sure that you have understood the things that I have discussed today. I have prepared a sample problem. Pay attention because later on you will be solving physics problems on your own. So for this point, at this point, this will serve as our practice. Pay attention and try to understand as I read the problem. So a motorcyclist is heading west through the small city called Lucena. So it accelerates after it passes the signpost marking the city limits. his acceleration is constant and is said to be 4.0 meter per second squared. At time t equals 0, he is 5 meters away from the signpost. And now he's moving 15 meters per second to west. So your task, or our task, is to find the position and velocity of the motorcyclist at time where t is equal to 2 seconds. And then afterwards, part B, we are required to find where the motorcyclist is when it's moving, or when it is moving 25 meters per second. First, it might look intimidating, but if we try to understand it and follow the procedures, we will not be lost along the way. According to the problem, the motorcyclist has a constant acceleration, so we can use the formula for constant acceleration. And based on the data that we have the acceleration, and the description, it is constant, and the variable that we use is ax, because we are going to use the positive x-axis, and it has its value 4 meter per second squared. Alright, so other values or other quantity that is present is the initial position, velocity, initial time, and final velocity. So you can look at it, and you will see the values right here and the variables that I have used. You can use a diagram to illustrate the problem. Right, and by making use of the data that we have, we can make this diagram more meaningful. So I'm going to use a Cartesian coordinate plane, and its origin will be represented as the signpost. Alright, so away from the signpost is the motorcyclist, which is said to be 5 meters away from the origin. Alright, and this happens when t is equal to 0 seconds. At that point in time, we start the clock. Alright, so the motorcyclist is now moving, and it has a velocity of 15 meters per second. Alright, so according to the problem, the motorcyclist has a constant acceleration, and it has a value of 4 meters per second squared. Now it is moving, so after 2 seconds, we are asked to find where the motorcyclist is and what will be its velocity. And later on in part B, because it is accelerating, there will be a change in velocity. Now, suppose that there is a point in time wherein the velocity is equal to 25 meters per second, we are going to look for the position of this motorcyclist along the x-axis. Alright, so all we have to do now is to solve for part A, right, which asks us to find the position of the motorcyclist after 2 seconds. We can use the formula x sub 2 is equivalent to x sub 1 plus vi times time plus 1/2 at squared. And once we plug in the values, and that is 5 meters for x sub 1, and then 15 meters for vi, and time is 2 seconds, and we have the acceleration as 4 meters per second squared. And once we execute this, you will get 43 meters. The motorcyclist is accelerating, there will be a change in velocity. Now what will be its velocity after 2 seconds? We can use the formula. Final velocity is equivalent to vi times acceleration times time. Alright, so the final velocity will be 15 meters per second plus 4 meters per second squared times 2 seconds. And once we execute it, we'll find that after 2 seconds, the motorcyclist is getting faster, and it's now moving 23 meters per second. See, I have two solutions. The first one is a little bit complicated, alright? So, but we are not going to explore that yet. We are going to explore the simpler one. A simple solution starts with the formula. df is equivalent to vi plus a times time. Alright, so we know that after quite some time, it will become, or the velocity will become 25 meters per second. That will be our final velocity. Alright, and 15 meters per second is a given data, which will be our initial velocity. We already know that the acceleration is constant, it's not changing. Alright, so, and that's 4 meters per second squared. Alright, so we can derive for time. Alright, so transposing this to the other side, we'll get 25 meters per second minus 15 meters per second, and dividing both sides by 4 meters per second squared will give us the value of time, which is 2.5 seconds. So, after 2.5 seconds, the velocity of this motorcyclist will be 25 meters per second. That we know the time, we just have to plug it in our formula, which we have used earlier, which is x of 2 is equivalent to x of 1 plus vi times time plus 1 half at squared. Alright, so by plugging the formula or the values, we have x of 2 is equivalent to 5 meters for x of 1, and then vi is 15 meters per second, and then time is 2.5 seconds, and then acceleration is 4.0 meters per second squared, and then following this formula, we will get 52 meters, or 55 meters rather. So 55 meters is the distance from the origin after 2.5 seconds. Okay, so we have found out that the motorcyclist is 43 meters away from the origin at time equals 2 seconds. So at that point in time, the motorcyclist is moving with a velocity of 23 meters per second. We are also asked about the position of the motorcyclist when it is moving 25 meters per second. And we have found out that when it is moving 25 meters per second, it is at 55 meters away from the origin. Okay, lastly, finally, we have to evaluate whether this result makes any sense. Alright, so sort of a reality check. Okay, so according to our results in part A, the motorcyclist accelerates from 15 meters per second, which is our initial velocity, and we convert it to kilometers per hour. We will find out that it is 54 kilometers per hour. And then it accelerates to 23 kilometers per hour after 23 seconds. We convert it again to kilometers per hour, and we'll find out that it's 83 kilometers per hour. And from 54 became 83. That means our motorcyclist gains much speed. Alright, so it becomes faster. Alright, so that's not all. Alright, so after 0.5 seconds, it accelerates again to 25 meters per second. And that's 90 kilometers per hour. Alright, so imagine after just 2.5 seconds, you were able to hit a velocity of 90 kilometers per hour. That is only possible if and only if you have a good bike, like Ducati, and then those top quality bikes, alright, high-end bikes, which cost around 700,000 to a million. Alright, so I hope I have a kind of bike like that. Alright, so I hope that you were able to enjoy the lessons that I have prepared for today. The time is now running low, and I have to say goodbye. Alright, so but I'm gonna be sending you a link of the sample graph that you have to work on, and you're going to submit it tomorrow. Alright, goodbye class, see you tomorrow. Hello guys, welcome back to the university, and if you are new to our channel, please click the subscribe button and hit the notification bell to get updated whenever we post new videos or new lectures about physics, about mathematics, about chemistry, biology, and earth science, and probably about school subjects, about the subject matter that you encountered in school. It will ensure that you will have good grades from now until the future. Alright, so let's dive into it and explore the concept of free fall motion. I hope you are familiar with high structure like this, wherein some daredevils or stuntmen are trying to jump from the top of the building or top of this structure, and once they jump, they are under the influence of gravity, and hence they are in a state called as free fall motion. So once they jump, there are variation in their weights. The question is, which one will fall first? Lighter objects, like this, face mask, or heavier objects when dropped at the same height? I hope you are able to see the results. Alright, so does air resistance matter? If there are variations in the result, you will reason out because the face mask is lighter or the feather is lighter and there is strong wind and so on and so forth. So we are going to explain all of that here in the university. Alright, so and you will notice that there is a difference in their speed. Alright, so is it constant? If it is constant, what is the constant value? We are also gonna determine that. And since this is about physics, you will expect a little bit of mathematics. And we are going to determine the equation or formulate the equation that will describe the free fall motion accurately in a mathematical manner. Answers to these questions are determined experimentally. Alright, so one famous experiment was conducted on the moon during the Apollo 15 mission by the astronaut in the person of David Scott in the year 1971. He had performed the hammer and feather experiment on the moon. So if you are on the moon and if you're gonna drop a feather or a hammer and the hammer simultaneously, the question is which of the two will hit the surface of the moon first. So if you want to know the result of the experiment, I'm gonna leave the link below, which is this one, http://www.archive.org/details NIX 15 1998 blah blah. Alright, so you just have to visit that and you will know the result of the experiment. Alright, moving on. We define air resistance as the force of friction. So when we say friction, it tends to oppose or to slow down the fall of a certain body. So air resistance matter because it counteracts the force of the acceleration due to gravity. So there is a big factor. So air resistance is a big factor. On the surface of the earth, if we are going to drop a hammer and a feather on the same height, the hammer will fall first because it is not so much affected by air resistance. On the contrary, our feather will fall later or slower compared to the hammer because it is largely affected by air resistance. So air resistance is a big factor. So we tried to answer the next question, which is which object will fall first, lighter object or heavier object? This experiment was, or the answer to this question was determined by Galileo Galilei in 1564 to 1642 in the Leaning Tower of Pisa. Okay, so on the top of this particular leaning tower, he conducted the cannonball dropping experiment wherein he dropped several types of cannonballs, small cannonballs or lighter cannonballs and heavier cannonballs. Alright, so both of them are spherical in shape, so the effect of air resistance is minimized. So he has found out that there is just a little discrepancy on the results. He must have concluded that there is a particular constant value of acceleration due to gravity. And how can we determine the value of this constant acceleration? Alright, so during those days, we do not have the complicated clocks or watches to get the time. So what Galileo did is vary the experiment and create a certain time measuring tool of interval, and he used the fluid. Alright, so as a clock. And to control the ball or the motion of the ball in one path, and to determine the length of the path, he used a certain inclined plane. So he tried to get the distance traveled by this particular ball along the ramp. with respect to the flow of the fluid. So that is how ingenious he is, because we do not have accurate clocks during those times, or stopwatches during those times. He had devised another way on determining the rate of distance traveled by the ball to the rate of flow of the particular fluid. So Galileo played on his setup. Okay, so he tried to vary the height or the starting point of the ball and measure the distance. Okay, so that is traveled with respect to his ingenious clock, which is the flow of water. And he has found out that after repeating such experiments, he always found that the spaces traversed by the ball is always equivalent to the square of the times, and yeah, it is all true for all the experiment. Meaning to say, it is proportional to the length of the time traveled, time squared, and a certain constant. And we are going to determine that particular constant in the next mathematical analysis. So if we are going to repeat the experiment today, having the complicated clock and timing apparatus or measuring apparatus, we can gather this data. Alright, we have the distance and we have the time traveled, and we can graph it. Alright, so we are going to pay attention to the table here. Distance 0 meter at time equals 0, then 5, 20, 45, 80, 125, and 180 respectively. And once we graph it, we show that the graph of this is a parabola, and it concludes that we are indeed dealing with a quadratic equation. Okay, so using the data and a little bit of mathematic tricks, okay, so we can see that this is the time covered, or that has passed by, and this is the distance covered, and the distance covered seems to follow a certain pattern, and in mathematics this is called a quadratic sequence. And a quadratic sequence has a first difference and second difference. Okay, so we're gonna get the first difference, that is 20 meters minus 5 meters, and that's gonna be 15. And we're gonna do it with 45 and 20. We're gonna do it with 80 and 45, and 125 and 80. So those are the first difference: 5 meters, 15 meters per second, 20 meters per second, 35, and then 45. And then we're gonna get the second difference, that is 15 minus 5, 25 minus 15, which is 10, 35 minus 25, which is 10, and 45 minus 35, which is 10. Okay, you will see that the second difference is constant, and that is around 10 meters per second in this graph, or yeah, so in this analysis. But actually 10 meters per second is the value of acceleration due to gravity, or yeah, so only the unit is wrong. So here we have found out that there is a particular constant which is equivalent to, or nearly equivalent to, 10 meters per second. So we're gonna do a little bit of mathematical analysis again to formulate the exact equation using the quadratic equation. So according to Galileo Galilei, so he have found out that the distance traveled is proportional to a certain constant and to the square of the time. Okay, so that is equivalent to distance traveled times, or equal to second difference because we found out that that is the constant. Alright? So, according to our data table and using the quadratic sequence analysis, that is the constant, and that is multiplied to the time. So, from this observation, we are going to formulate our equation. Okay? So, we can write it as d, or distance traveled, for d is equal to k, which is the second difference, times k. K is a constant. I just call it a constant like that. And plugging the observation by Galileo, so it is equivalent to this one, t squared, or the square of the time. So the question is, what is the combination that will lead it to be equal to 5? So I can do it by introducing a constant called as 1/2, and then 10, and then t squared. So if we're going to substitute it for a value of 1, so that is 5 is equal to 1/2 of 10, which is 5, and then 1 squared, so that is 5 is equal to 5. So our formula is now equivalent to d is equal to 1/2 k squared. Alright, has a value of 10, or that is our value of acceleration due to gravity. So we can write it as d is equal to 1/2 gt squared. So that is how we formulate the equation for the free fall motion. So to wrap things up, okay, so the value of g is equivalent to the second difference, which is it has a constant value of negative 9.8 meter per second squared. So why negative? The negative sign there indicates that it is directed towards the center of the earth. And you can also use the formula pi squared. Alright, so if you square the value of pi, it will have the value of 9.8. 9.8. Alright, so square pi and you will get your formula. Okay, so generalization, air resistance plays an important role in Earth. Alright, so but in places wherein there is no air resistance, doesn't matter. Okay, so weight of the object does not matter. Okay, because it's not included in the formula. So whether heavier or how heavy the object is or lighter the object is, it will fall. It will reach the bottom of the ground at the same time. Alright, just like doing that. And yeah, so in the absence of air resistance, lighter object and heavier object will fall simultaneously. Alright, so I hope you guys were able to understand this lesson. Okay, before we move on to the complex part, which is heavily problem solving. I hope you guys were able to understand the basic concepts of free-fall motion, because that is very important in physics. Alright, so if you want more videos about physics, about this, and you like my explanation, please click the subscribe button and hit the notification bell to get updated whenever I post new videos or lectures here in the university. Bye bye guys, see you soon, see you next time.